Hello students, in today's chemistry class, we are going to discuss class +1 chemistry topic Hess's Law from the unit Thermodynamics. Myself, Lakhbir Singh, lecturer chemistry, Sipahi Jaswant Singh, Government Senior Secondary School, Pasod, Turi, Sangrur. In the year 1840, Russian chemist Germain Henry Hess proposed a generalization regarding the enthalpies of various reactions, and this generalization is known as Hess's law of constant heat summation. Hess's law deals with enthalpy changes. Enthalpy is a state function. Its value depends upon the state of the system and is independent of the manner by which the state has been attained. In chemical reactions carried at constant temperature and pressure, both the reactants and the products have certain definite enthalpies associated with them. The change in enthalpy delta H can be expressed as the difference in the enthalpies of the products and reactants. Enthalpy of reaction is equal to enthalpy of products minus enthalpy of reactants. The value of delta H is positive if enthalpy of products is greater than enthalpy of reactants, and its value is negative if enthalpy of products is less than enthalpy of reactants. Thus, change in enthalpy delta H is the heat energy exchanged between the system and surroundings at constant temperature and pressure. Let us understand this law by taking an example in which a system changes from initial state A to final state D by two paths. In path 1, initial state A directly changes to final state D with enthalpy change delta H. In path 2, initial state of the system A changes to final state of the system D by 3 steps. In step 1, initial state A first changes to intermediate state B with enthalpy change delta H1. Intermediate stage B in the second step changes to another intermediate stage C with enthalpy change delta H2. Intermediate stage C then changes to final state of the system D with enthalpy change delta H3. In this example, according to Hess's, when the system changes from initial state A to final state D, the total enthalpy change remains the same whether the reaction follows path 1 or path 2. That is, total enthalpy change in path 1, which is equal to delta H, will be equal to total enthalpy change in path 2, which is equal to delta H1 plus delta H2 plus delta H3. Thus, the total enthalpy change remains the same for a given reaction whether the reaction follows path 1 or path 2. Now, statement of Hess's law of constant heat summation. It states that the enthalpy change or heat evolved or heat absorbed in a particular reaction is the same whether the reaction takes place in one step or in a number of steps. When we represent Hess's law graphically, it becomes even more clear that change in enthalpy depends only on the initial and final state of the system and is independent of the path followed by the system to change from initial state to final state. Hess's law can be justified with the help of law of conservation of energy or first law of thermodynamics, according to which energy can neither be created nor destroyed. Let us suppose Q joules is the total heat evolved when reactants changes to products directly by path 1 and Q dash joules is the total heat evolved when reactants changes indirectly first to intermediate compounds and then to products. Therefore, Q dash is equal to Q1 plus Q2. Let us further suppose that Q dash is greater than Q. This means that when reactants change to products by path 2 and the products are converted back to reactants by path 1, Q dash minus Q amount of energy will be evolved or created. This is against the law of conservation of energy or the first law of thermodynamics. Thus, Q dash cannot be either more or less than Q. The two values must be same. That is, Q dash is equal to Q or the Hess's law is true. A chemical equation in which heat energy change during a reaction is also mentioned is known as thermochemical equation. From Hess's law, we can conclude that the thermochemical equations can be added, subtracted, or multiplied like algebraic equations to obtain the desired equation. As is given in the example, the total enthalpy change in path 1 delta HR will be equal to total enthalpy change in path 2, that is delta H1 plus delta H2 plus delta H3. After understanding Hess's law, let us discuss its applications. We will discuss applications of Hess's law under 6 headings. Number 1, determination of enthalpy of formation of substances which cannot be measured experimentally. Number 2, calculation of standard enthalpies of reactions. Number 3, determination of enthalpy of transition. Number 4, calculation of bond energies. Number 5, calculation of enthalpy of hydration. And number 6, predicting enthalpies of various reactions. The heat energy change or enthalpy change that accompanies the formation of 1 mole of a compound from its constituting elements at a given temperature and pressure is called enthalpy of formation. With the help of Hess's law, we can find out the enthalpy of formation of compounds such as methane, carbon monoxide, benzene, etc., where a direct determination is not possible experimentally. Let us understand this by taking example of enthalpy of formation of ethane. The required equation is 2 carbon plus 3 hydrogen giving you C2H6. We are given 3 equations. First equation is the formation of carbon dioxide from carbon and oxygen. Enthalpy change for this reaction is delta H1 equal to minus 286 kilojoule per mole. Second equation is the formation of water from hydrogen and oxygen. Enthalpy change for this reaction is delta H2 equal to minus 393.5 kilojoule per mole. Third equation is the combustion of ethane forming 2 carbon dioxide plus 3 water. Enthalpy of this reaction is delta H3 equal to minus 1560 kilojoule per mole. As in the required equation, carbon and hydrogen are on the reactant sides and there are 2 moles of carbon and 3 moles of hydrogen. So we add first and second equations and we multiply first equation containing carbon by 2 and also multiply delta H1 by 2 and it comes out to be minus 572 kilojoule per mole. Second equation is multiplied by 3 as in the required equation there are 3 moles of hydrogen and its enthalpy value delta H2 is also multiplied by 3 and we get minus 1180.5 kilojoule per mole. Third equation is subtracted because in the required equation ethane is on the product side and its enthalpy value delta H3 will also be reversed and it becomes plus 1560 kilojoule per mole. So when we add these equations we will get required equation 2 carbon plus 3 hydrogen giving you C2H6. Similarly, when we add the enthalpy values we will get the enthalpy of formation of ethane which comes out to be minus 192.5 kilojoule per mole. In the second example, let us calculate the enthalpy of formation of methane. So the required equation is carbon plus 2 hydrogen forming methane. We are given enthalpy of combustion of 3 reactions. First reaction is carbon plus oxygen forming CO2. Enthalpy of combustion delta H C1 is equal to minus 393.7 kilojoule per mole. Second reaction hydrogen plus half oxygen forming water. Enthalpy of combustion delta H C2 is equal to minus 285.7 kilojoule per mole. Third reaction methane plus 2O2 forming carbon dioxide and 2 water. Enthalpy of combustion delta Hc3 is equal to minus 890.3 kilojoule per mole. In the required equation we have carbon plus 2 hydrogen on the reactant side, so we add first and second equations and we multiply the second equation by 2 and also multiply delta H C2 by 2 which comes out to be minus 571.4 kilojoule per mole, and third equation is subtracted because in the required equation methane is on the product side, so enthalpy of combustion delta H C3 also changes to plus 890.3 kilojoule per mole. When we add these three equations, the molecules that are not required will cancel out, like oxygen, carbon dioxide and water. We are left with carbon plus 2 hydrogen forming methane. Similarly, when we add the enthalpy values, we will get enthalpy of formation of methane which comes out to be minus 74.8 kilojoule per mole. Second application, calculation of standard enthalpy of reaction from standard enthalpies of formation. The change in enthalpy that accompanies the formation of 1 mole of a substance from its constituting elements under standard conditions of temperature, normally 25 degrees centigrade, and pressure 1 atmosphere, is called standard enthalpy of formation. The knowledge of standard enthalpies of various compounds can help in calculating the standard enthalpy of reaction. It is the difference in the sum of the standard enthalpies of products and reacting species taking part in the reaction. Thus, standard enthalpy of reaction is equal to standard enthalpy of formation of products minus standard enthalpy of formation of reactants. Calculation of standard enthalpies of reactions. Example 1. Ethene gas plus HCl gas give you ethyl chloride gas. Calculate standard enthalpy of this reaction. Given 3 equations and their corresponding enthalpy of formations. First equation is the formation of ethene from carbon and hydrogen, and enthalpy of formation value delta HF1 is equal to plus 52.2 kJ per mole. Second equation, formation of HCl from hydrogen and chlorine, enthalpy of formation delta HF2 is equal to minus 92.3 kJ per mole. Third equation, formation of ethyl chloride from carbon, hydrogen and chlorine, enthalpy of formation delta HF3 is equal to minus 109 kJ per mole. From these 3 equations we have to derive the required equation. In the required equation, ethene and HCl are reactants, but in the first and second equations we have ethene and HCl as products. So first we subtract these equations 1 and 2 and their corresponding enthalpy of formation values are also changed. Delta HF1 becomes minus 52.2 kJ per mole and delta HF2 becomes plus 92.3 kJ per mole. Third equation is added. Now when we add these equations and their corresponding enthalpy of formation values, we get the required equation ethene plus HCl gas giving you ethyl chloride gas. The molecules that are not required in the final equation will cancel out, as carbon cancels with carbon, hydrogen cancels with hydrogen and chlorine cancels with chlorine. From the enthalpy of formation values we can calculate standard enthalpy of this reaction, which comes out to be minus 68.9 kilojoule per mole. Second example, methane plus 2 oxygen give you carbon dioxide plus 2 water. Standard enthalpy of reaction is required. We are given standard enthalpy of formation of carbon dioxide, water and methane. By using the relation standard enthalpy of reaction is equal to sum of standard enthalpy of formation of the products minus sum of standard enthalpy of formation of the reactants, we can calculate standard enthalpy of this reaction. Now, carbon dioxide and water are products, methane and oxygen are reactants. So when we put the values, standard enthalpy of reaction becomes sum of standard enthalpy of formation of the products, that is enthalpy of formation of carbon dioxide plus 2 into standard enthalpy of formation of water minus sum of standard enthalpy of formation of reactants, that is minus standard enthalpy of formation of methane minus 2 into standard enthalpy of formation of oxygen. When we put the values, we can calculate standard enthalpy of this reaction, which comes out to be minus 890.3 kilojoule per mole. Third application, calculation of enthalpy of transition. Many nonmetals like carbon, sulfur, phosphorus exist in a number of allotropic forms. The enthalpy of transition is the change in enthalpy when 1 mole of allotropic form of a substance changes to the other and vice versa. The change is very slow and the amount of heat energy exchanged is so small that the value cannot be determined experimentally. However, the enthalpy of such transitions can be calculated theoretically with the help of Hess's law. For example, calculate enthalpy of transition of carbon diamond to carbon graphite. We are given two equations. First equation, carbon diamond combining with oxygen forming carbon dioxide, enthalpy of formation is equal to minus 395.4 kilojoule per mole. Second reaction, carbon dioxide decomposing into carbon graphite plus oxygen, enthalpy of this reaction plus 393.5 kilojoule per mole. From these two equations we want to derive the required equation, so we just add these two equations, so the molecules that are not required in the final equation will cancel out. Oxygen, carbon dioxide cancel out, and when we add the enthalpy values we get the enthalpy of transition of carbon diamond to carbon graphite, which comes out to be minus 1.9 kilojoule per mole. Fourth application, calculation of bond energies. The amount of energy required to break 1 mole bonds of a particular type between two atoms in the gaseous state of a substance is called bond dissociation energy, and the average of the bond dissociation energy of the bonds of the same type in a gaseous substance is called bond energy. The enthalpy of a reaction may be given as the difference in the bond energies of the reactants and products participating in the reaction. Enthalpy of reaction delta H is equal to sum of bond energies of the reactants minus sum of bond energies of the products. Example 1. Hydrogen combines with fluorine giving you 2HF. We are given hydrogen-hydrogen bond energy 432 kilojoule per mole, HF bond energy 565 kilojoule per mole, enthalpy of formation of HF minus 269 kilojoule per mole, and we want to calculate fluorine-fluorine bond energy. So, in the equation, one hydrogen-hydrogen bond is broken, one fluorine-fluorine single bond is broken, and two HF single bonds are formed. By applying Hess's law, delta H reaction can be calculated from the bond enthalpy of reactants and bond enthalpy of products, and by substituting the values, enthalpy of reaction can be calculated from the enthalpy of formation by multiplying it by 2, because in the required equation we are having 2 moles of HF. So all the other values are known to us, so we can calculate bond energy of fluorine-fluorine bond, and which on calculation comes out to be 160 kilojoule per mole. Second example, carbon monoxide gas combines with water gas forming carbon dioxide gas plus hydrogen gas. We are given bond enthalpies: carbon oxygen bond in carbon monoxide, carbon oxygen bond in carbon dioxide, oxygen hydrogen bond, and hydrogen hydrogen bond. We have to calculate enthalpy of this reaction. As you know that in the reactants, carbon oxygen bond breaks in carbon monoxide and two OH bonds in water break to form carbon dioxide, in which two CO bonds are formed, and hydrogen, in which one hydrogen-hydrogen single bond is formed. By using the relation enthalpy of reaction is equal to sum of bond enthalpy of reactants minus bond enthalpy of products, we can calculate enthalpy of this reaction after substituting the values of bond enthalpies of the reactants and products, and the enthalpy of this reaction comes out to be minus 41 kilojoule per mole. Fifth application, calculation of enthalpy of hydration. The change in enthalpy or heat energy when 1 mole of the anhydrous salt changes to a hydrated salt by combining with specified number of moles of water is called enthalpy of hydration. With the help of Hess's law, we can find the enthalpy of hydration of either an anhydrous or partially hydrated salt. It is very difficult to find its value experimentally. For example, we can find the enthalpy of hydration of copper sulfate from given two reactions whose enthalpy of solutions are given to us. When we apply Hess's law, we can calculate enthalpy of hydration of copper sulfate, which comes out to be minus 78.2 kilojoule per mole. Hess's law can be used for the determination of various other types of enthalpies also, which cannot be determined experimentally. It is used in research where the industries use this law to develop the most effective methods to produce the products. According to Hess's law, same amount of energy will be released in our body during burning of food. Let us summarize what we have studied today. We studied Hess's law, which states that the enthalpy change in a particular reaction is same whether the reaction takes place in one step or in a number of steps. Then we studied applications of Hess's law under 6 headings. First, determination of enthalpy of formation of substances which cannot be determined experimentally. Second, in the calculation of standard enthalpies of reactions from the standard enthalpies of formation. Third, in the determination of enthalpy of transition. Fourth, calculation of bond energies. Fifth, calculation of enthalpy of hydration and predicting enthalpies of various reactions. Hope you have all understood the topic and enjoyed the class. Thank you.